Oh, what a day! What a lovely day!
Welcome to Science versus Scientism. I'm your host, Nathan Oakley, and if you're new to this channel, or you have not done so already, be sure to subscribe and hit the bell notification icon to keep up to date with the Flat Earth debate. If you would like to support this channel, there is a super chat that runs alongside the show while it's live, and a link in the info box below the video once it's rendered. I am joined by John, otherwise known as YouTuber Quantum Eraser, and we will later on in this presentation get to the namesake of John. So how are you doing, John? Good to have you here.
Very good, sir. Thanks for having me again.
Pleasure. I think this is probably the most excited I've been about one of your presentations. I'm not going to lie. It was absolutely mind-blowing when you went through it with me the other day.
Yeah, I have a lot of fun with it too. It's my passion.
I mean, you've also presented this on Cathexis channel, so has the presentation changed much since you did it last time?
Yeah, I added a few different things in there. It's, I could go on for about, 20, 25 hours. So I switched it up a little bit, kept it current, and concentrated on a few more areas and dropped a couple areas. So let's see how it goes.
Cool. Well, without further ado, let me know when you're ready and I'll stick you up on screen.
Yeah, go ahead. Let me know when it's up.
Yep, ready to go.
All right, so before we get into the main event, I'd like to stay here for a couple minutes. It seems that on both camps, people just aren't getting this. So let's stop here. So again, paleontology, anthropology, archaeology, geology, evolutionary biology. Yeah, I'm still laughing. Theoretical physics, that's non-experimental. And then our genre, astrophysics, astronomy, and cosmology. These guys, these are not friggin' sciences. Um, I don't I don't know how to say this any differently, but they're just not sciences. I don't know what I should do. Maybe get it notarized or something. I don't know. These guys can't perform experiments. So they're not sciences. If you can't perform experiments, then it's not science. It's just as simple as that. But I don't know. We just get people in here talking about these as sciences. Why? They're just, it's by fiat, just the name. Crocheting is more scientific than these clowns combined, right? The first six pretenders, these guys, they can't even get into the scientific method. That's science. Observe a phenomenon. They can't get there without a time machine, right? The final three masqueraders, like I said, the ones in our genre, I mean, they can't formulate scientific hypotheses because they lack viable independent variables. It's just that simple. They can't isolate and test and validate their dependent variables or their predictions. A scientific hypothesis, it's a hard stop. It's over right here. Now, the true sciences are quantum mechanics, that's physics, genetics, chemistry, biochemistry, and biology. And remember, there's a caveat with these guys also. Each claim from any of these disciplines must be accompanied by experiment, preferably repeated, validating each claim. Now, if one of these guys come out, let's say from quantum mechanics or any of these guys, with a claim without experiment validation, well, you can dismiss that claim. However, you can't dismiss the discipline, right? You're not throwing the baby out with the bathwater here. You just dismiss that claim that's not supported by experiment and you move on. Everything else is good. If no experiment, that equals codswallop horsepucky. It's just that simple. So do not fallaciously indict the actual sciences as pseudosciences, as these guys, right? They're not the same. I mean, I even ran into a post the other day, and I'm sure we've all run into these throughout the past 3 years. Well, what do you got to say about the technology of the past 100 years? Well, I don't have to say too much about it, right? because that technology was afforded by what? It just happened to coincide with the development and advancement of quantum mechanics. Well, I don't have a problem. We're good to go. I mean, we're not talking about these guys, are we? Are they trying to somehow take some veracity from quantum mechanics and put it onto these guys? What? Show me the MRI that geology has provided, right? Or the laser from cosmology. Right? It ain't going to happen. So it's quite ridiculous. And maybe this will help. I don't think so, because I've been saying this for 3 years now. It's both camps too. Well, our war is against science. Really? Your war is against these guys. Best wishes. Because the door's going to close on you pretty quickly. So if you want a war against these guys, that's fine. Because these are pseudoscience pretender clowns. All right. Quantum mechanics. Utter these two itty bitty words to the majority of people and witness firsthand this, right? We've all seen this before. I'm not talking about the pretender clowns. I'm talking about, you just regular everyday Joes. Sometimes I'll do it, around family gatherings, a whole bunch of people's around or friends, and I'll just bring up the term or the phrase quantum mechanics and just observe people. I'm not going to talk anything about it. I just want to see their reaction, right? Even with people that don't know what these two terms mean, right? I'm going to get this look or a rolling of the eyes. Even grandmothers, right? They'll be shaking their heads. They haven't even heard of these terms before. Talk about a conditional response, right? Where'd they get that from? Why is that? Most neither have the time nor the inclination to bother with such things. But for the laymen who informally tread into this area are immediately confronted with numerous barriers, right? There's background noise, mathematical formalism, snake oil prognostications. Even if you go the formal institutional route, 99.9999% of the time of your undergraduate and graduate level studies will fall immediately into this category, right? Shut up and calculate. Richard Feynman coined this term. So, Professor Nicholas Geeson from the University of Geneva. In short, then, the mathematical formalism of quantum theory provides no explanation. How many times have I talked about this? Mathematics can only describe. It can't explain anything. It can only describe the what. It can't give you the how or the why. This gives the how and the why. So, again, in short, then, the mathematical formalism of quantum theory provides no explanation, only a way of doing calculations. Some physicists conclude that there is nothing to explain. Shut up and calculate, they would advise us. But wait a second, this is physics. We need explanations, not descriptions. Any idiot can describe something. We need explanations, we need demonstrations, we need illustrations, preferably with experiment. That's what physics is. We're talking about science here. Well, there's a method to their madness. Since the majority of scientists, which most professing are not, have an a priori adherence to their fairy tale religion, philosophical naturalism, realism, that's atheism, which is scientifically falsified, by the way. We're going to get to that. The irrefutable experimental evidence in the literal thousands without exceptions of quantum mechanics, the most successful branch of physics in the history of science, stands in direct contradiction to it. Puts them in a very difficult and uncomfortable position, vice-like. You can either reckon with the scientific evidence, and there's boatloads of it, and adjust your worldview accordingly, or close your eyes, put your fingers in your ears, and say, la, 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 shut up and calculate over and over again, and let cognitive dissonance rule the roost. Then what you do is you start erecting barriers and begin labeling it as quantum, weirdness, spooky, strangeness, absurdity, paradoxical, bizarre. You're going to hear these terms in the literature, in the scientific literature. That denotes a fringe science, which is the exact opposite of what it actually is. It surely is all of those if you're wearing philosophical, naturalist, realist, or atheistic glasses. Take them off. But no, can't have that. They then conjure and float up mind-numbing interpretations. What is this, religion? Right? There's no interpretations in science and the scientific method. It's black or white. It's a 1 or a 0. So this is nonsense right from Jump Street. You know, they got ad hoc and rescue hypotheses. The most popular one is the many worlds or multiverses, right? Well, that's like conjuring invisible three-toed gnomes. Many worlds, show me another world. That's what I thought. It can never be confirmed or falsified. So use it as a get out of incoherent jail free card to cloak their mind-numbing adherence to fairy tales with the facade of science, which are merely clumsily contrived just-so stories, to obfuscate having to give account for their ludicrous scientifically falsified stance. They're busted, and they know it. So let's go here. Richard Feynman. He's pointed out that every statement in quantum mechanics is just a restatement of Heisenberg's uncertainty principle. Well, what did Warren Heisenberg have to think about all this? And again, I had this on the last presentation. The first gulp from the glass of natural science will turn you into an atheist. But at the bottom of the glass, God is waiting for you. He knew this. All these guys knew this back then. They knew more about the meaning of quantum mechanics back in its infancy than they do now. It's astonishing. I mean, the computation power has increased exponentially. However, about the meaning, they were all over this back in the day. So basically, the uncertainty principle states that the more accurately you know, that's going to become very important here in a few minutes. The more accurately you know the position of a particle, the less accurately you know the momentum of that particle, and vice versa. So let's get to it. I'll be talking about photons to limit confusion, but everything I discuss applies equally to all elementary particles, electrons, atoms, and molecules. So in 1801, Thomas Young shot a coherent light source through a double-slit experiment, and this is what he got. All right? This isn't a model. It's not a prediction. It's just what he got. Right? Another important point here. You see these terms down here, interference and diffraction, right? They're synonymous. They mean the same thing. This is a diffraction pattern or an interference pattern. This is going to become very, very important here in a few minutes. Keep your eye on that. So from 1801 up through 1910, 1915 area or so, all they got was this pattern. So everyone just assumed light was a wave. That was it, right? But 2 consecutive Nobel Prizes were awarded in 1921 and 1922. Why? Well, each showed conclusively photons were actually particles. The photoelectric effect and Compton scattering. Now, I've whipped Einstein around by the short hairs for the last 10 or 12 years, but give credit where credit is due. You see, Einstein didn't receive a Nobel Prize for those fairy tales, general and special relativity, which aren't scientific theories anyway, by the way. He received it for this, the photoelectric effect, and it's well deserved. All right, so credit where credit is due. And Compton scattering, this experiment right here, it was the death knell. It sealed the coffin shut. Photons are particles. So from the chair of physics at Yale, everything is really particles. All things, electrons, photons, protons, neutrons, they are all particles. So let there be no doubt about that. Okay, there's no doubt about it. So, let's take a look at this. These are rocks over here. This is waves. This is rock. or rocks, and in here are individual rocks or particles, and this is a wave, right? Hopefully everyone understands this. They're mutually exclusive. Now, if you're confused about this, go ahead and ring your call button. I'll have Tommy come back and hit you in the head with the tack hammer. So these are particles. This is a wave. For example, if you stand 3 feet away from me, I pick up a pebble and I hit you in the forehead, it's going to hit you in a distinct spot on your forehead, right? That's a particle. However, if I pick up a bucket of water and throw that on your face, the energy from that wave, from that water wave, is going to be spread out across the entire transverse dimension of that wave. It's going to hit you all over your face instead of one distinct spot. Now, we all know this intuitively. So, but we're poor, dumb animals, so let's have a scientist reconcile this, see what his thoughts on. So, Leonard Susskind, professor of physics at Stanford. Particles are particles and waves are waves. How can a particle be a wave? Wave in an ocean, that's not a particle. The ocean is made out of particles, but the waves in an ocean are not particles. Rocks are not waves. Rocks are rocks. So a rock is an example of a particle, and an ocean wave is an example of an ocean wave. And now somebody is telling you that a rock is like an ocean wave? What? So, hey, credit where credit is due. At least he realizes the nonsense here, right? I mean, it's over. However, what do we get? Well, we get wave-particle duality, right? Well, we just went over that you can't have that. And everyone knows this, right? It's like cerebellums or facultative anaerobe woodpeckers, right? They're incompatible. But that's what we get. So when this phrase, wave-particle duality, is uttered, what they actually mean is collective particles contrived wave-like non-duality. That's what they actually mean, and I'm going to show you why over the next few minutes. This is really important. I can essentially stop right here, really. I know you guys won't let me do that, but I could stop right here. From the chair of physics at Yale. So we have to play this game in two ways. It is particles, but its future is determined by a wave. But, and that's a very big but, the wave is purely mathematical, right? What's he talking about here? Well, he's talking about the wave function, Schrodinger's wave function or wave equation. You cannot put an instrument to measure the energy due to that wave. It's a construct we use to determine what will happen in this experiment. It's it right there. I can stop. But I won't. Where's the fun in that? So the double-slit experiment results. These are typical patterns you get from the double-slit experiment, right? You got the interference or diffraction. Remember that one now. Interference and diffraction, the same thing. And when you have photon slit detectors or detectors at the slit and you have the knowledge of the which path information, well, you get this pattern. So all are actually particles here. If you look real close here, what you'll see is there's discrete chunks of energy and momenta, i.e. a particle, that hits this photographic plate, right? If you could zoom in here on this interference pattern, you're going to see the same thing. There are particles hitting here. So the argument isn't over whether particles are hitting these detectors. Everyone knows this, right? It's the overall pattern that's the issue. The overall pattern, that's the game. Now, even if I fire one photon at through the double slit without any detectors, even one photon, let's say I fire one photon every hour for 20 years, this pattern is waiting for me. Even with one photon. You can have a stream, you can have trillions of photons, or one photon at a time, it doesn't matter. You're getting this pattern. Now, what is this? What does this look like? Right? It's a probability distribution. That's all it is. Again, it's the overall pattern that we're concerned with. And number 4, the Schrodinger equation. Now, What he did was reverse engineer this interference pattern. They got thousands of these patterns over and over again. Now, I'm not trying to diminish or slight Erwin Schrödinger for what he did. I mean, it was yeoman's work to come up with this wave equation, and he received the Nobel Prize for it. As a graduate, he did this as a graduate student. But what he did was reverse engineer this interference pattern. It's essentially a mathematical description of the superposition. It's a probability distribution, is what it is. We've all seen these before. Listen closely. This is very important. Again, from the chair of physics at Yale, you cannot mathematically derive any of quantum mechanics except looking at experiments and trying to see if there is some theoretical structure that will fit the data, right? That's what Schrödinger did. That's the textbook definition of what he did. Quantum mechanics, it's a theory which is based on experiment. It's not deduced by mathematics. So you see the dichotomy here. Experiments versus mathematics, and mathematics versus experiments. They're not the same thing. This is science. This is mathematics. Hopefully this is understood. I doubt it. So again, back to the interference pattern, right? It's just a probability distribution. Like we talked about before, we've all seen these histograms, probability amplitudes, probability distributions. That's all it is. And like I said, even if I fire one photon, every hour for 20 years, this pattern is waiting for me, right? Now, on these predictions, they're not scientific predictions. They're statistical predictions based on this pattern. So let's say I fired 1 million photons at the double slit, and someone stops me and says, okay, for the millionth and first photon, I want you to tell me where it's going to go. I can't tell them where it's going to go. Nobody on this plane can tell them, right? All we can say is that when the wave function is high, the probability is high, there's a good chance of it's going to hit here. And as the probability gets lower, it gets less and less. And when the probability or the wave function is 0, then you're not getting any photons here. Okay, so this is a statistical prediction. It's not a scientific prediction. Now, divining wavelengths. This is the game. So divining wavelengths from particles. And this S is very important here because they're not divining a wavelength of a particle. I'm going to show that here in a few minutes. It's particles. Now, this is a scale diagram showing what pattern you get from single slit diffraction down to 7-slit interference. Now, as you can see here, what's happening, as you increase the number of slits, the more defined and discernible this pattern is becoming, right? This is really easy to discern this. Now, instead of 7 slits, let's put 1,000 slits per millimeter. So what do you guess is going to happen to this pattern, right? It's going to get uber distinct and defined, and you can easily measure through here, right? So let me introduce you to diffraction grading, or better said, right, interference grading. This is going to be an interference pattern, right? So what they're going to do is they're going to take this monochromatic light source, fire it at the grating or the double slit, and in this case, it's thousands of slits per millimeter, right? They're going to fire them over to this detector, and what's going to happen? Well, we already know what's going to happen, right? We're going to get an interference pattern, but we're going to get distinct dots, right? We know this from the 7-slit. So what they do is, when they manufacture a wavelength of particles, that's important. What they do is they fire this monochromatic light source at this diffraction or interference grating. They take the number of slits, then they take the distance between the diffraction grating and the detector, then the angles here between the 0 order, 1st order, 2nd order, and 3rd order. Then they take the distance of these dots, right, between the 0 order and then the mean values of the 1st order, 2nd order, and 3rd order between these guys. And voila, what pops out with a little trig? The wavelength. But wait a second. This is an interference pattern. The interference pattern is governed back here by the wave function. But we already discussed that the wave function isn't real. So you're getting a wavelength, something real from something not real? What? And remember, this is particles right here, right? We can debunk this real quick. With one particle, I want a wavelength for a particle. So what I'm going to do, I'm going to put the most premier physicist right here. I'm not going to have him look back here at me. He's going to look at this detector. I'm going to come back here with a laser. I'm not going to tell him what color it is. I'm going to fire one photon through this diffraction grating. It's going to hit this detector. My question to him, give me the wavelength. Right? He's going to look at me like I have 35 heads, and rightfully so. It's a nonsensical, inane inquiry. He's not going to be able to do that, right? This is a begging the question fallacy, right? It's a convention is what it is. Now, is the convention right or wrong? I mean, no, it's the question's malformed. Conventions aren't right or wrong, they're just conventions, right? So the problem arises when you come outside the boundaries of the convention and make a statement based from the convention on reality. You can't come out here and say, oh, that, well, the wavelength of this light is 400 nanometers. And so we're going to come out here and say, well, particles are waves. No, you can't say that. It's a begging the question fallacy. It's prima facie, right? And I already showed you with the one photon, he's not giving me any wavelength, right? It's just a convention. It's used for communication, right? If somebody says 400 nanometers, or you read it in scientific literature, 400 nanometer light, well, everyone knows that's UV light. There's no problem with that. I have no issue with it. But it's when you come outside that convention and make statements or knowledge claims about reality, you can't do that, right? We all know that. So when they manufacture a wavelength, and that's exactly what they did, well, then frequency is a cakewalk, right? Because frequency is nothing more than the speed of light over the wavelength, or lambda. Well, we already established that the wavelength, that's a begging the question fallacy convention from above. And the speed of light is also a begging the question fallacy convention. We're not going to talk about that here. Maybe in a future presentation we might get into it. But what you got here is the begging the question fallacy sandwich. That's all you got. I mean, this is over. There's no argument against this. So like I said, the interference or diffraction pattern is birthed or governed by the wave function. But the wave function isn't real. It's only a contrived concept. That's all. Therefore, this whole exercise is only a contrived concept. You have to go back to its roots, right? It's just a convention. And like I said, I already showed you that with a photon, with a single photon. And again, like I said, this is collective particles, right? So collective particles, trillions of particles are being fired here. Contrived wave-like, right? They contrived a wavelength from this convention into reality, right? Non-duality. That's what it is. Collective particles, contrived wave-like non-duality. And let me give you the electromagnetic spectrum. Through visible light, the whole thing from radio waves, right, through gamma rays, this is all photons. There's no question here. And what are photons? Well, they're particles. It's over. To summarize, a particle is a particle and a wave is a wave. There are no wavicles or paves. There's only two ways to magically endow a particle with a wavelength, then frequency, right? And that's even inane, prima facie. We only have a particle. So we have the wave function, that's Schrodinger's equation. We already talked about that. That's not a physical wave. And B, the diffraction or interference grating. This is a contrived convention because this is based on the wave function. It's over. It's over. There's no argument here. You can't even conceive of an argument against this. It's end the story. By the way, as a result of these conclusions, the 1929 Nobel Prize in Physics needs to be rescinded. I'm sorry, the one awarded to Louis de Broglie, right? What Louis
It's
said
worth
was,
pointing that out again, John. Just
say again?
debunked a Nobel Prize winner.
Yeah, the 1929 Nobel Prize in Physics went to Louis de Broglie. Yeah. What was your question?
Just pretty much debunked him, right?
Yeah. Now listen, this guy was brilliant, right? I'm going to tell you what he did. See, like I said, they had all these interference patterns, and then he figured out interference, the wave patterns. Well, photons were actually particles. So what he did was he postulated, well, if light, which we thought were waves, is actually particles, then what if what we think are particles, like electrons, neutrons, or protons, have wave-like attributes, right? That was pretty ingenious to do that. And by the way, he was a graduate student at the time also. Seems like these graduate students have a little more leash than everyone else. But anyway, that's what he postulated. So what did they do? Well, they sent electrons through the double slit. Guess what happened? They got this pattern, right? This is an interference rate to happen. The photons and the electrons acted the same way, and everything acts the same way, like I said in the beginning. But that's what they got. They sent it through a double slit. Well, this is a diffraction pattern, right? What did we talk about with this diffraction? So guess what they got? It's electron diffraction grating. That's how they pop the wavelength out for particles. Well, we already told you that this is a begging the question fallacy. Convention, it's just a convention. There's nothing wrong with that, like I said. The problem only arises when you come out of the walls of that convention and make statements based on the convention into reality. It's nonsense. Begging the question fallacy. Textbook. So I'm sorry, it's over. There's no argument against this. So, before we move on, listen, debunking this wave particle duality stuff has no effect whatsoever on quantum mechanics. None. Zero. So this isn't really that big of a deal. But we have to cross the I's or dot the T's. Cross the I's and dot the T's. That's what we're doing. So let's move out of this convention and let's deal with reality. So the nature of our reality, right? So Richard Feynman again, he's pointed out that the entire mystery of quantum mechanics, well, it's in the double slit. Well, thanks a lot, Richard. I mean, that narrowed the field down for us, didn't it? What he's saying there is, let's get rid of all these lines, all this stuff back here. What he's saying here is, if you understand what's going on in this experiment, well, you understand quantum mechanics. He also said that nobody understands quantum mechanics. What? I understand this double slit experiment. I showed this to my daughter 5 years ago when she was 10. Took her about 15, 20 minutes. She got it. She was asking poignant questions about it also. So I don't know. Richard Feynman's pretty intelligent guy. I'm sure he got it. Well, see what the problem here is. Richard Feynman was what? He was a professed atheist. Now, what did I tell you in the beginning of this presentation? See, you can't understand this willfully. You cannot understand what's going on here, because if you do, then you're at odds. You're directly contradicting your worldview. Atheism, they're irreconcilable. Quantum mechanics and atheism are married bachelors. You can't do it. So what do you have to do? Well, you have to be willfully ignorant of this. He certainly understood this, without a doubt. So, like I said, let's get rid of these lines here. Let's virginize this experiment. Nothing's on this back plate back here. What quantum mechanics experiments have validated is that as soon as this photon is fired from here, right? From here to the detector, until it hits this detector, there is no photon here. You think I'm crazy? There's nothing here, folks. I'm telling you there isn't. You think I'm out of my mind? Okay. From Werner Heisenberg, the atoms or elementary particle themselves are not frigging real. They form a world of potentialities or possibilities. Now, what are we talking about here? We're talking about the wave function. Potentialities or possibilities. That's what the wave function is describing, rather than one of things or facts. From Professor Anton Zellinger, the path taken by the photon is not an element of reality. We are not allowed to talk about the photon passing through this or this slit. Neither are we allowed to say the photon passes through both slits. All this kind of language is not applicable. Right? And on a personal note, this guy right here, it's a crying shame that he hasn't been knighted with at least one Nobel Prize. By my count, it should be 3. Listen, you can't get into this genre. You can't get into quantum mechanics, especially the experiments, for 30 minutes and not run into this guy's name over and over and over again. I mean, I don't even know who number 2 is. Number 2 isn't even in the galactic vicinity. So to set the record straight, right? So back to the double slit experiment results. So what is going on here, right? What are these results telling you? You know, the difference between these results. Now, we already talked about the particles are hitting this. That's not the issue. We're looking at the overall pattern. So what is this telling you? Well, it's telling you, let's go with the interference pattern first. It's telling you that if there was no detector here, that the photons were acting like, very important, like waves, non-physical waves. That if there was no detector here, you wouldn't get anything here. Nothing's existing here. As opposed to this pattern, you know, we have the knowledge of the which path information. Well, what's this pattern telling us? Well, that the photons acted like, you know, baseballs before the double slit, through the double slit, past the double slit, and hit the detector. They did exist. It's like taking baseballs, chalking up baseballs, you know, get a big double slit and fire 500,000 baseballs through back to the backstop, a black backstop. This is what you're going to get. I mean, a lot of people, when they look at these, they don't see, you know, the ramifications, but that's what it means. And again, it's the overall pattern that's the issue here. Not that particles are hitting here. Everyone knows that they're particles hitting. The problem, if they're Newtonian particles, and every particle is a Newtonian particle, we should only see no interference. We should only see this. But we see interference to the right. Well, that's a problem. Right? What are they when we're not looking, or better said, knowing? That's the key. And why is it when we look or measure or to know where they are before they reach their destination, that's the photographic plate or the emulsion plate, the pattern changes and we get a standard particle pattern here to the left? Why is that? So again, this is the typical double slit. Over on the right-hand side, Young's typical double slit experiment. There are no slit detectors in this experiment. It's just virgin. He's going to fire a coherent light source, and he's going to get an interference pattern on this back wall. But, you know, after those experiments by Einstein and Compton and a few others, they said, well, wait a second. You know, photons are particles. Why are we getting this interference pattern back here? We shouldn't be getting that. Now I'm going to skip a lot of experiments, a lot of time here, but eventually they said, okay, there's something going on at these slits. Let's figure this out. So they put photon detectors here, right? Gathering the which path information. They were storing the information. And what happened? Excuse me. Well, the wave function collapsed. That's what they say. That's how they phrase what happened, the difference between the interference pattern and the two columns. The wave function collapsed, right? And they're saying, well, wait a second. I mean, we just put photon detectors here. Why is it changing the overall pattern? It doesn't make any sense. But it's really cool because there are only 2 choices left here why this wave function is collapsing. right? One's obvious, one's not so obvious. But the first one is, well, the photon detectors are somehow or in some way interacting with these photons coming through this through these slits and changing this pattern, right? Or number two, it's not so obvious. It's the path information. It's knowledge, it's knowing that's collapsing this pattern. So that's pretty cool. There's only two choices. We're looking at only two choices in a cause and effect relationship, right? Well, that's pretty easy now. We can test this. We got this down. We can deal with this. So you had two camps. Either the photon detectors are causing wave function collapse, or knowledge of the which path information is causing wave function collapse. There are only two choices. It's black or white. It's a 1 or a 0. No interpretations here. It's either this or that. So, before I get to this key point, this is a really good point right here. Let's go back up here because there's a lot of confusion out there. We don't want to add confusion. We want to take away confusion. So when people get in these discussions, what happens here is they don't differentiate and provide a distinction between photon detectors or electron detectors or whatever detectors at the double slit and this plate back here, this photographic plate. This is what I call a catcher's mitt, right? That's how I differentiate them because all it's doing is catching these photons or whatever is being fired through the double slit. So be careful when you're in these discussions, go ahead and delineate what you're talking about, right? Because there's so much confusion with detectors this, detectors that. I was in a few discussions. I just dropped the discussion. I said, we're so far off the main point, there's no sense in going on. So go ahead and do that. It'll limit confusion. So back to our two questions, right? Well, the quantum eraser experiments and more of the delayed choice experiments were designed to settle the question on the mechanism for the wave function collapse, mainly the quantum eraser part of the experiment. Most of these experiments were thought experiments. They were the brainchild of Professor John Wheeler at Princeton. He thought up all these experiments, but back in the day, they didn't have the technology to deal with them, right? They couldn't actualize them. However, as we're going in time, 70s, 80s, and 90s came along, they said, well, hey, we can actually actualize these thought experiments. And they did. Good news for us. So that brings us to a delayed choice quantum eraser, right? I call this the undisputed. It's undisputed on many levels, and my namesake. And this was by Marlon Scully and Yunhoo Kim in 1999. And the reason why I call this the undisputed is that any conjurings that anyone feebly dreams up to obfuscate quantum mechanics is clobbered incessantly over the head with this experiment alone. I mean, there's not an argument, there's not a single one in 10 years that I just didn't go into this quantum eraser and just pummel anyone's arguments. That's why it's undisputed, or one of the reasons why. The second one is the simple elegance of this experimental design. You're going to see it here in a few minutes. It is quite noteworthy. I've seen thousands of experiments, and this one just stood out to me. Over many different disciplines, this one really stands out. It's simple elegance that stands out. And number three, the magnitude of the downstream ramifications of what this means for our reality will leave you breathless. I mean, it's quite amazing, and you're going to see that here in a few minutes, hopefully, where you don't have a pulse. So ever since this experiment, this is another funny thing, ever since this experiment was published and continuing to this day, has sent and continues to send physicists in droves to the Eastern mystery religions, right? Why? Well, there's no way out. I mean, if you're an atheistic scientist and you understand quantum mechanics or have been around the discipline, you can't reconcile it with your worldview. So it sends them in droves. You can even go through the literature and find them talking about this, right? They won't go to Christianity. We can't have any of that. So we have back to our cause and effect relationship. We have two choices. well, if we have a cause and effect relationship and we only have two choices, what can we do? I know, excuse me, almost choked. I know, let's do the scientific method. The pollen's not helping here either, man. We got like a quarter-inch of pollen outside on my Jeep, so it's pretty bad. But listen, we can do the scientific method, right? Let's do an experiment. So observe a phenomenon. Photons, elementary particles, atoms, molecules exhibit both wave-like, that's interference patterns, or particle behavior, no interference pattern. Step two, the alternative hypothesis. If the which path information is known or can be known, then we will observe wave function collapse. That's no interference. Conversely, the null hypothesis. If the which path information is known or can be known, then we will not observe wave function collapse. In other words, if the which path information is not known or it's erased and never can be known, then we will observe interference. That means the wave function's intact. Now, if the environment is the mechanism for wave function collapse, they call it decoherence. That's interaction quanta with a physical measuring device, in this case slit detectors, then we will not observe any change in pattern between the downstream detectors. I'll show you those here in a few minutes. The independent variable in this experiment is inside the experimental setup. It's based on the paths. It's either the known paths, and that's detectors D3 and D4, and the unknown paths, detectors D1 and D2. The dependent variable is, well, whether we're getting interference patterns or no interference patterns. Just that simple. Excuse me. So, test experiment. Remember the two camps now. Don't lose sight of this. Don't forget the question. The two camps for the cause of wave function collapse, it's either the slit detectors or knowledge of the which path information. Now, this is the experiment. This is kind of small. Let's go to a bigger version so you can see it. Now, at first blush, this is pretty complex, right? It's pretty intimidating. But if you take your time, get the Adderall drip out, right, and go through this experiment, identify all the players and what's going on here, like 5, 10, 20, or 500 times, you'll get this. It's actually, after you get it, it's really quite simple. And like I said, simple elegance. Let's go through it. We'll go through it slow. So we got the laser beam, the light source back here. It's an argon pump laser. You have the double slit right here. You have a BBO crystal and a Glan-Thompson prism, right? Now, before we move on, notice something I didn't mention over here, right? What didn't I mention over here by the double slit? There are no slit detectors here, right? So we're testing this hypothesis directly. There are no slit detectors in this experiment, okay? So let's move on out. D0, D1, D2, D3, and D4, along with D0. All these guys, all these black rectangles here, are catcher's mitts. They're only catching these photons. That's all they're doing. You got another prism here that's guiding these photons on their paths. These green things right here are beam splitters. Now, they're half silvered mirrors. That is to say that any photon incident on one of these beam splitters, there's a 50-50 chance of the photon either transmitting through or reflecting off. Okay? MB and MA are full silver mirrors. They can only reflect 100% of the time any photon that's incident onto them. And you have the coincidence counter, right? This is storing all the information from this experiment. Another important thing, this is a fire and forget experiment. That is to say, you could turn this experiment on, leave the lab, go on vacation, and you're good to go. There are no observers in this experiment. Very important, right? No observers. You don't have to observe anything for this experiment to come to fruition. Okay? So let's go through a path. So we have the argon pump laser here. It fires a single photon at a time through the double slit. Hits this BBO crystal. Now, it converts that single photon into two entangled photons. The signal and the idler, they're sister photons. This Gland-Thompson prism separates those entangled photons and sets them on two different paths, one to D0 and the rest through this part of the experiment. Now, we're not going to pay any attention to D0 for right now. Let's just be concerned with what's going on down here. So, a photon is fired, and D4 gets a ding. It gets hit. So, but what can we say happens if D4 gets hit? Well, what we can say is we know the path information, right? It can only come out of the A path or the red path. We'll call the red path A path. There's no way a photon can be fired out of the B path or the blue path and hit D4. So we know the path information. The same thing happens with D3. Due to the experimental setup, if this detector is hit, the only way it can be hit is if it came out of B. There's no way a photon fired out of slit A can hit D3. The same, there's no way that a photon fired out of slit B can hit D4. There's just no way. The experimental setup limits that, right? So now we move on to D1 and D2. This is the eraser part of this experiment, D1 and D2. Or better said, it's the obfuscation part. Excuse me. What's happening here, the path of these photons are taking is erased or obfuscated by the experimental setup, right? As for D4 and D3, the photon can take only one single path, but with D1 and D2, it can take both paths. Watch. A photon fired out of slit A can transmit through BSB, reflect off MB, reflect off BSC, and hit D2, right? A photon can also be fired out of slit B path, transmit through BSA, reflect off MA, transmit through BSC, and hit D2, right? So the path is obfuscated. It can come out of either slit. We don't know. We can never know. Every single time a photon hits D2 or D1, guess what happens? We get an interference pattern here. It's acting as if, very important part, as if, because we don't know the path information, it's giving us an interference pattern here. Guess what happens at D4 and D3? We get wave function collapse every single time either one of these detectors are hit, right? This is over. It's over. Our question's over right here. There are no slit detectors. The wave function collapses because knowledge of the which path information, right? Yeah, but we're not done yet. That's pretty cool, but that's not the jaw-dropping part just yet. Let's go back to D0. So, photon gets fired, split into two entangled photons. The sister photons, one sister goes here, the signal photon. The other sister photon, the idler, goes on its path. Well, this detector is hit 8 nanoseconds before any of these detectors are hit in this experiment. In fact, this detector is hit by one of the sister photons before its sister reaches these beam splitters. It's right in this area or right in here. Guess what happens? Every time D0 displays a wave function collapse or no interference pattern, its sister hits D4 or D3. Every single time, there's no exception. Every single time D0 registers an interference pattern, its sister photon hits D2 or D1. We're off the reservation here. You know, if your jaw didn't hit the floor just now, you need to check your pulse, because we're off the reservation. This photon knew where its sister was going before it got there. Right? Now, either this photon got a highly complex computer on board, or Edgar Casey or Gene Dixon are riding this photon, then we're off the edge of the map. I mean, take your time and savor this, right? Let's go back to the experiment, right? And deal with the experimental results and leave you with that. Well, this is easy, right? The results of this experiment are easy. The unknown paths, we got interference patterns. The known paths, we didn't get interference patterns. If we had wave function collapse, it's over, right? Right? The slit detectors versus knowledge of the witch path information, it's over. It's knowledge of the witch path information. Done. End of story. Analyze the results. Well, we just did. Let's go through it formally. As you can see with the results above, the witch path information coming from either slit A or slit B was erased, obfuscated, or lost by the experimental setup for R1 or R2. Don't let this confuse you. It's D0 and D1 with D0 or D1 and D2. So D0 in combination with D1 and D2. So the photon acted in a way as if it went through both slits. It displayed an interference pattern, and it's the same pattern as a traditional double slit experiment without slit detectors. For R3 and R4, the witch path information was known due to the experimental setup. It displayed no interference, the same pattern as the traditional double slit experiment with slit detectors. Since there weren't any slit detectors in this experiment, that is, the slit A or slit B path information was either known or unknown merely by the experimental setup for each of the downstream detectors. Well, this is easy right now. Step 5, validate or invalidate the prediction, right? Well, the alternative hypothesis is validated. There is no possibility that the slit detectors collapsed the wave function. Why? Well, because there weren't any. Therefore, the prediction is confirmed. Knowledge of the witch path information solely collapses the wave function. The null hypothesis is rejected or falsified. Decoherence is incoherence. It's over. So the experimental conclusions. The existence of the witch path information alone causes wave function collapse. Decoherence, physical interaction with the measuring devices, does not cause wave function collapse. And quantum mechanical phenomena transcend time and space. That is, space-time is bunk. That's why Einstein tried to debunk quantum mechanics, because it was debunking him. He was the antagonist. We needed him, right? He was the canvas used to paint this picture, right? Sorry about that, but he got debunked. Well, additional confirmation. I picked 3 out here. I can, pick hundreds now, but the one that stands out is this one, Zhao Sung Ma, from the Proceedings of the National Academy of Sciences, 2013. The quantum erasure with the causally disconnected choice. This experiment not only confirms and validates the delayed choice quantum erasure, but validates the time component by 5 orders of magnitude and the space component by 50 orders of magnitude. Their detectors were like 144 or 45 kilometers apart. But this is over. See, the gobsmacking implication here are that not only are there no slit detectors at the double slit, but again, time and space or space-time is utterly meaningless in this reality. And how in the world did the sister signal photon know where its sister idler photon was going before it got there? How did that happen? Interdimensional Jedi telepathy? And number 2, how in the world can photons know the witch path information? Aren't photons inanimate objects? I mean, they're not sentient, intelligent beings, are they? And why act differently even if they did know? I mean, this is preposterous anyway. They don't know anyway. So somehow the photon knew that you knew where it came from and where it was going to end up before it ended up, and changed its behavior accordingly. What's that sound like, right? Sounds a whole heck of a lot like omniscience, doesn't it? It's just jaw-dropping. It's Unbelievable. See, these guys knew this stuff even before these experiments came out. These guys knew it. Check us out, 1986, from Professor John Wheeler. Right? It begins to look as we ourselves, by our last minute decision, have an influence on what a photon will do when it has already accomplished most of its doing. We have to say that we ourselves have an undeniable part in what we have always called the past. The past is not really the past until it has been registered. Or to put it another way, the past has no meaning or existence unless it exists as a record in the present. That's why Niels Bohr said, no phenomenon is a phenomenon unless it is an observed phenomenon. Sound familiar? First step of the scientific method. Let's take a little sidebar here. That means all the fairy tale just so story prognostications, for example, radiometric dating, or any dating method for that matter, by the metaphysical pseudoscience priests telling us what happened in the past. You know, remember these guys, these clowns, right? We talked about before. These claims are all cod-swallop horsepucky, validated by experiment. You can't get around this. Again, in 1986, Sir Rudolf Peierls. The moment at which you can throw away one possibility and keep only the other is when you finally become conscious of the fact that the experiment has given one result. You see, the quantum mechanical description is in terms of knowledge, and knowledge requires somebody who knows. You gotta have it. We live in a virtual construct. I don't want to hear it. You know, from the snowflakes out there. This is what these experiments are telling us. Unless you can show photons and electrons, you know, having sentience and intelligence, I'm sorry. There you are. There it is. Who's the programmer? You got to have one. Who's the knower? You got to have one, right? So, in conclusion, in order for matter to exist, there must be a knower first. That's why I've been saying this for 10 years. Now you see the reason why. And atheists, pay attention. From Bernard de Espinal, The Quantum Theory and Reality, in 1979. Great year, by the way. The doctrine that the world is made up of objects whose existence is independent of human consciousness. Well, what is that? Well, that's philosophical naturalism, realism, and atheism. That's what it is. That's what this is. That's the quintessential tenet of it. Turns out to be in conflict with quantum mechanics and with facts established by experiment, right? Who's the science deniers again? Can't hear you. Let me break this down for you. Phlogiston, 13th century alchemy, and Alice in Wonderland are more tenable than your fairy tale scientifically falsified religion. Atheism. Make no mistake, this is a religion. It's belief without evidence, or the lack of belief without evidence, right? It's not only that. In fact, it's belief without evidence in the face of scientifically falsified experiments, right? The evidence scientifically falsifies your position here. That's more than religion. That's blind, fanatical, religious zealotry. This is you, right? Take a good look at you. No way around it. Let's pile on. So, from New Scientist, and this paper is dealing with the parent paper from Nature down here. We'll get to it here in a moment. In 1967, Simon Cochin and Ernst Specker proved mathematically, and we'll get to that here in a few minutes, that even for a single quantum object where entanglement is not possible, the values that you obtain when you measure its properties depend on the context. So the value of property A, say, depends on whether you chose to measure it with property B or with property C. In other words, there is no reality independent of the choice of measurement, right? That's it. And notice these, right? They kind of stand out. I painted them differently for you. Chose, the choice. What are they talking about here? Free choice, free will. That's what they're talking about, right? The only two doctrines that I know of that speak to free choice as quintessential tenets of their doctrines is quantum mechanics and Christianity. Just saying. So, this was in 1967. They came up, they proved it mathematically, right? Then, in 2011, Lapquik's experimental non-classicality of an indivisible quantum system from Nature. The authors showed that unlike what one would expect if reality were independent of mind, realism, that's philosophical naturalism or atheism, the properties of a quantum system do not exist prior to measurement via validating the Cauchy-Specker theorem. Renowned quantum physicist, here he is again, Anton Zellinger, in a related New Scientist article dated June 2011, suitably titled "Quantum Magic Shows Reality is What You Make It," is quoted as saying that there is no sense in assuming what we do not measure about a system has an independent reality. Conclusion: no knower, no matter existing. Again, there is no sense in assuming that what we do not measure about a system has an independent reality, Zellinger concludes. Cochin, now at Princeton University in New Jersey, is also happy. Almost half a century after Specker and I proved our theorem, which was based on a thought experiment, real experiments now, it's very important, confirm our results. See, before the real experiments, all you had was a fairy tale. That's it. But real experiments now confirm our result. Steinberg, quantum physicist, is impressed. This is a beautiful experiment. If previous experiments testing entanglement shut the door on hidden variable theories, the latest work seals it tight. It appears that you can't even conceive of a theory. You can't even conceive of one. You can't even imagine one, let alone actualize it, where specific observables would have definite values that are independent of the other things that you measure. It's over. Conclusion: no knowery, no mattery. So let's wind it up. I don't think that people actually appreciate the delayed choice quantum eraser, so I'm going to break it down into a simple double-slit example. Right? So let's get this right. Let's pull this up. There we go. So let's say you just got promoted to physicist of the world. University has given you your own lab. So, and again, let's say get rid of all these lines and stuff. You're going to virginize this experiment. You decide that, hey, you've listened to this quantum mechanics junk for, many years. So you decide, hey, I'm going to do the experiments myself. I want to see this. I'm going to confirm this myself. So what you do is you set the experiment up. You put slit detectors. You want to be comprehensive, so you put slit detectors here, slit detector here, right? You're going to route this path information over to a computer here, all right? And then you're going to run this experiment. You run this experiment 499 times, right? Every single time you run this experiment, the wave function collapses. That is, there are two bars or two patterns behind each of these slits every single time, 499 times, right? So you're tired, time to go on vacation, Jamaica mom. So, but you have one experiment left to run. Well, you say, oh, the heck with it. I'll run the experiment while I'm gone. It ain't going to make any difference, right? So you clean up this experiment, put a new photographic plate over here. Now, instead of routing the information from these slits to this computer here, you're going to route the information, the slit information, over to the administrative building, over to your computer over here, right? So what you do is you turn this experiment on. You don't look back. You don't look at the experiment. You flick the switch. You turn this experiment on. No looking back. You close the door and you lock it. Now, you have the only key to the lab. The custodians, janitors, they don't have the key. You are the only one with the key. No one can enter this room, right? And over here in the administrative building, no one can enter your room. Your office is closed. That's it. It's going to stay dirty. And you're going to Jamaica for 3 weeks. So after 2 weeks, the experiment, runs its course. Either the light source burns out or you have it on the timer or whatever. It burns out, it's done, right? So you stay another week in Jamaica and it's time to come home. So you get on the plane. During the plane flight, your secretary calls you and says, hey, the building's on fire, the administrative building. So you get off the plane, you run on over to the administrative building, the building's total. It's done. All your path information that came from this experiment is destroyed. It's irretrievable. It existed, now it doesn't exist. No one looked at it, right? It's gone. You're bummed out that the building burned down, but you say, hey, well, the glass is half full. I still have my lab. It's good to go, right? And you already know what's going to happen over here, right? Because you did this experiment 499 times. Every single time you got wave function collapse, right? You got 2 columns behind here. So you head on over to the lab. You walk into the lab, you open up the door, you look at this detector, and guess what you see? That's what you see. Interference, baby, right? I'm telling you, that's what he's seeing. That's what that quantum eraser experiment was telling you. Now, we're off the edge of the map here. Out here, there be monsters. There's a new sheriff in town, and his name's a delayed choice quantum eraser. Y'all be cool. Right on. Thanks for your ear. Have a nice day.
Absolutely superb. Really, really good presentation. Is there anything else you need to add? I don't think there is anything you need to add, but I've always got to ask, of course. That's the way of these things.
I don't know. I don't know. Maybe with this one, to add something, I don't know what I could add to it. This is jaw-dropping right here, right? Now listen, let's try another scenario, right? You have the path information existing over here, right? But the custodian can come in here, into the lab. If a custodian comes into this lab and he looks at this detector with the path information existing, no one knows it yet, right? But it's existing in this reality. If he walks in to this experiment, he's getting wave function collapse here. That's it, right? He's getting wave function collapse. That's it. It's over, right? There's nothing to convert it back. Once he sees it and he knows that there's 2 columns here, it doesn't matter what happens to this path information. It can burn, it can get destroyed. It doesn't matter. It's already done. Nature folded it. It didn't fold its card. It has lay its cards on the table, and that's it. It's irreversible or irreconcilable. It's 2 columns.
Yeah, likewise, although you didn't say this when you gave the example, but it's sort of assumed that if it didn't burn down, the same thing.
Right. I think we talked about another example. What was it on the? Oh yeah, it was the beach, right? So another good example. Nathan and I, we go to the beach. Now we're the first people ever to go to this beach. No one has ever been there before, and we both look out and we see an island. Right there is an island out there, and like I don't know, 5 miles off the beach, we see the island. Both of us see it. It's there. However, we leave the beach and we get in a car accident and we die. Now, no information is existing in this reality that island exists, right? So let's say Sally, she decides to come down a couple hours later. She's on the beach and she looks out. That island doesn't have to be there. It doesn't. It's a probability distribution. It's just a draw. You take a draw from nature. It's off that interference pattern, right? Remember I said about the probability distributions, right? I know it's out of this world, but that's the way our reality is.
That's you need to know it. It also answers the age-old question: which came first, chicken or egg?
Right. The chicken.
Gonna have Noah.
Emphatically.
So, very interesting questions to get answered with the things like the quantum eraser. I think I might round it out there, John. It's been an absolute pleasure. Thank you very, very much indeed for going through that presentation with us. It really was exceptional, as always.
It was my pleasure, sir.
And I'm also going to say a massive, huge, enormous thank you to all of the live audience for tuning in and hopefully for sharing this presentation. If you haven't done so already, be sure to like, comment, share and subscribe. I've been Nathan Oakley and I will see you all in the next video.
Oh, what a day! What a lovely day!